Hi, welcome to class. My name is Don Lafond, Professor Don, and this week in Cisco 1, we are covering Module 6, the data link layer. Now, I will make a separate presentation for Module 7. Module 7 is closely related to Module 6, and you might hear a lot of the same things because we're talking about the same area of the OSI model, the last two levels of the bottom two levels of the OSI model, the physical and data link layer. We'll get into that. If you have any questions, please hold your questions until the end of the presentation if you're here with me live. If you're watching this as a recording in our NetAcad class, please put your questions in the help discussion forums. And if you're watching it on YouTube, please ask your questions if you have any in the comments below. And I also encourage you to answer your own questions there as well and answer each other's questions there. That community can be quite vibrant if you guys help out, and I appreciate that. I'm going to go ahead and share my screen. And there's a couple things I have to do to set this up. I have to start the presentation, start the chat room. And I need to do something over here. A little bit of setup. Appreciate your patience. And we are ready. The data link layer. All right. So we're going to talk about how media access control in the data link layer supports communication across networks. We'll describe the purpose and function of the data link layer. We'll compare the characteristics of media access control methods on WAN and LAN topologies. And we'll describe the characteristics and functions of the data link frame. The purpose of the data link layer. So the data link layer is responsible for communication between end-to-end networking interface cards, NICs. It allows upper layer protocols to access the physical layer media and encapsulates the layer 3 packets, IPv4, IPv6 packets, into layer 2 frames. It also performs error detection and rejects corrupt frames. I'm going to zoom in on this picture so you can see it a little bit better. So remember, layer 2 is NICs, destination NIC and source NIC. We're going to talk about MAC addresses in this presentation. And then layer 3, that's the Ethernet layer. I'm sorry, that is the network layer. That has our source IP and destination IP. Remember, this does not change. This changes at every hop. I'll say that again about 3 more times in this presentation. So IEEE 02 LAN MAN standards are specific to the type of network: Ethernet, wireless LAN, wireless PAN, such as Bluetooth, etc. The data link layer consists of 2 sublayers: the logic link control, LLC, and the media access control, MAC. The LLC sublayer communicates between the networking software at the upper layers and the device hardware at the lower layers. The MAC sublayer is responsible for data encapsulation and media access control. And we'll talk about this, but let me show that to you. We're talking about the data link layer. And I want you to also note that that's why I talk about the bottom 2 layers working together because it overflows into the physical layer as well when we're talking about the standards and actually sending the content over the line. Packets exchange between nodes may experience numerous data link layers and media transitions. For example, we talked earlier in the semester about mail leaving, or similar to the post office, where mail leaves, say, Atlanta, Georgia, and it's going to San Diego, California. It's going to go from one post office to another post office. Now it's also going, and each one of those is going to have a different MAC address, a different physical address for the post office. It'll have a different MAC address in subnetting. In networking. I'm going to turn down my volume. At each, also the media transitions, your mail, when you said something from Jacksonville, from Atlanta to, my example, Atlanta to San Diego, it may go by truck, it may go by little truck, big truck, it might go by plane, but it's going to be different media, just like your packet is exchanged between nodes, might go from wireless to physical, to copper, physical copper, to physical um, uh, uh, fiber, and then at the other end, maybe the last layer, maybe it gets to you through Bluetooth, right? So that is what happens from where the sender to the destination. Now, at each hop along that path, a router performs 4 basic layer 2 functions. It accepts the frame from the network medium. It de-encapsulates the frame to expose the encapsulated packet. It makes a decision about what to do with it, and then when it's heading the other direction, it re-encapsulates the data into a new frame, and then it forwards the new frame on the medium to the next network segment. I'd almost like to put 5 basic layers in there, because it does have to make a decision if it's going to send it back out. But those are the 4 things that it does. It accepts it, de-encapsulates it, re-encapsulates it, and then forwards it back out. All right, good. Now, the data link layer protocols are defined by several organizations, and I encourage you to learn what each one of these organizations do, and I also highly recommend that you make flashcards. Once you know the organizations and what they do, those questions are going to be easy questions for you on the CCNA exam. Topologies. The topology of a network is the arrangements and relationship of the network devices and the interconnections between them. There are 2 types of topologies used when describing networks. There's the physical topology that shows the actual physical connection, maybe a closet on a floor in a building, and it'll show how the devices are interconnected, from switch on floor 3 to router on floor 2, right? That's the physical. It actually shows location, if you will. Logical, on the other hand, identifies the virtual connections between devices using device interfaces and IP address. So instead of saying the switch is on the second floor, switch 2 is on the second floor, it would say the port IP address of 10.10.10.2 is connected to that switch, instead of the location of the switch, the actual IP address. That's what you get with logical topology. There are 3 common physical WAN topology, wide area network topologies. There's point-to-point, hub and spoke, and mesh. Now, point-to-point is the simplest and most common WAN topology. It consists of a permanent link between 2 endpoints. Hub and spoke, similar to a star topology, where a central site interconnects branch sites through point-to-point links. And then mesh provides high availability because everything is connected to every other device. It is, maybe you have a mesh system, a wireless system in your home. Everything talks to everything. In a wired mesh network, everything physically with a cable has to be connected to be able to provide true mesh capabilities. And in that case, anything could go down, but because you have a mesh, you have multiple connections, it's easily to reroute. Physical point-to-point topologies, for example, connect 2 nodes, in this case, 2 routers. The nodes may not share the medium with other hosts. So this network in the middle may have other types of connections between that we don't even talk about. We have, in this case, maybe a fiber connection out to our ISP, And then on the other end, we have a fiber connection going to node 2. It doesn't have to be fiber. It's just whatever the connection is, it could be wireless. The nodes may not share the media that it's on with other hosts. They're just talking about maybe you're using a laptop computer or a phone. That media, wireless media, is different than the media it's connected to its ISP. Because all frames on the media can only travel to or from the two nodes, point-to-point WAN protocols can be very simple. Now, here are some LAN topologies. You should have covered this previously in your hardware class, but I'll go through it. End devices on LANs are typically interconnected using a star or extended star topology. Star and extended star topologies are easy to install, very scalable, and easy to troubleshoot. Basically, you have I can zoom in. Basically, with these two types, they're basically the same thing. Here you would have a switch, and the switch would be connected to another switch, and then that's your extended star. And you could continue to connect to another switch, and then it could have a star. That is common today. For example, a classroom would be connected to a single switch, and that switch would have 24 ports and maybe 20, yeah, and then the instructor goes to a different switch, but it could be the same switch. Anyways, so these would be all the computers in a lab, and it's connected to another switch someplace that connects to other labs that have other star topologies. Now, these are the older technologies. They're legacy. Early Ethernet and legacy token ring technologies provide two additional topologies. There's bus. All end systems chain together and terminate on each end. Believe it or not, in my Navy days, we ran a bus topology from one side of the ship to the other side of the ship, and we ran through. We got in trouble for it, by the way. I was young and wild back in those days, and we ran physical cable, 10-base-T, through all of the waterproof connectors between rooms, and they didn't like that when they found out that we did it for gaming. We wanted to be able to be in different places of the ship and be able to be gaming all day long, or at least when we had free time. All day long. We're underway for 6 months. You have a lot of free time. Anyways, they had us rip it all out, which made no sense at all, because if you're ripping out all those cables, now you're actually leaving all those holes that you had to make to be able to run the cable, but whatever. The problem with a bus topology is if there's a break in a line, the whole system goes down. You have to have the endpoints. If either one of those are taken off, for example, if you're adding another node on the system, when you take this down, the whole network is down. When you take off an endpoint to add another node, the whole thing's down. Or if you break it anywhere in the middle, the whole thing's down. It doesn't work partial. A ring topology doesn't work partial either. Each end system is connected to its respective neighbors to form a ring, and a token actually is passed around this ring, and each node gets its time to respond to that token. That's why it's a slower system than, say, a star topology. The other problem with a token ring waiting for a token to be passed around the ring is if there's a break anywhere in that line, also nothing communicates. All communication is brought down until that line is repaired and the ring is complete again. So those are topologies. Now we talk about half and full duplex. Half duplex, think walkie-talkie, allows only one device to send or receive at the same time on shared media, wireless in this case, in the walkie-talkie. Actually, it is wireless, yeah. It's used on wireless LANs and legacy bus topologies with Ethernet hubs. half duplex, only one device can communicate at the same time. Now, in today's world, you can imagine that. What happens is the router, the wireless router, if you will, broadcasts a signal to everybody, that wireless signal that you have to sign into, right? Even if you're at Home Depot, for example, you sign into their wireless. They don't know you're out there until you sign in. Now, your device receives the broadcast, and then your device then broadcasts a repeat signal back or reply signal back, and then the router, wherever it is, picks up your signal. It's still a half duplex. They broadcast, you receive it, you respond, you broadcast, they receive it, and on and on and on. Half duplex. And we'll talk about how collisions are mitigated in half duplex. Full duplex, on the other hand, gigabit Ethernet, for example, is always full duplex, allows both devices to simultaneously transmit and receive on the same shared medium. Ethernet switches operate at full duplex mode. Now, how does half duplex deal with collisions? Well, it uses contention-based access. All nodes operating in half duplex competing for use of the medium. Examples are carrier sense multiple access with collision detection, CSMA CD, as used on legacy bus topology Ethernet. Now, carrier sense multiple access with collision avoidance is used on today's wireless LANs. That's CSMA/CA. Don't worry, we cover that on the next slide, what each one actually does. Now, that allows controlled access. So it's a deterministic access where each node has its own time on the medium. It's used on legacy networks such as Token Ring and ArcNet. Again, we don't cover that. We don't cover controlled access. So I don't have to say that long word again. Anyways, so here we're back to CSMA CD. It's used by legacy Ethernet LANs. It operates in half duplex mode where only one device sends or receives at a time. It uses a collision detection process to govern when a device can send and what happens if multiple devices send at the same time. Now, if it detects a collision, the devices transmitting simultaneously will result, if devices transmit simultaneously, it will result in a single collision on the shared media. The device detects the collision, and then devices wait a random period of time and then retransmit. If they just happen to pick the same random time a second time, then they just pick another random time and then they transmit again. That's CSMA CD. Now, CSMA CA, collision avoidance used on wireless LANs, operates in half duplex mode where only one device sends and receives at a time. It uses a collision avoidance process to govern when a device can send and what happens if multiple devices send at the same time. Now, this is the process. When transmitting, devices also include the time duration needed for the transmission. So other devices on the shared medium receive that time duration and know how long the medium will be unavailable. Sort of as in your walkie-talkie, if you were to say, I will be talking for the next minute, then the other person would just listen for a minute. They wouldn't want to talk at the same time. And also, at the end of a walkie-talkie, you say over. That also signals the end. Well, this doesn't signal an end. It actually tells you what the duration will be needed for the transmission. The data link frame. Now, data is encapsulated by the data link layer with a header and a trailer to form a frame. A data link frame has three parts: the header, the data, and the trailer. The fields of the header and trailer vary according to the data link layer protocol. The amount of control information carried with the frame varies according to the access control information and the local topology. We talk about that on this slide. So here on this slide, we see that they have added to our packet that is coming down from the network layer, we add to it a header. Now in the header, we add the frame start and frame stop. Then we add addressing information. The type, addressing information, this is the source and destination nodes. The type of data, IPv4, IPv6, and control, which indicates, identifies flow control services. This is like QoS and things like that. Then, which we don't really talk about yet. Then at the other end, there is detection, our CRC, that detects that there is a problem, and then the frame is dropped if there's a problem with the data itself. So this is what our frame looks like that we're placing out on the physical layer, out onto the internet. All ones and zeros, and off it goes. Now this is, I said we'd come back to this on our second slide of the presentation, the layer 2 addresses. So it's also referred to as the physical addresses because your NICs have MAC addresses, and those MAC addresses are the physical address. Each one is unique. Remember, a NIC, a network interface card, has a MAC address. That MAC address is unique, and we'll talk about it in this presentation, I think. If not, the next one. The layer 2 contains the frame header. It's used only for local delivery of the frame on the link, that meaning from one device to the next, and it's updated at each device that forwards the frame. So let's look closer at this. And I love this slide. I want you to remember this slide. We're going to see it again next week when we talk about the network layer. The network layer, they want it to be so much more complex, but you can get the network layer by just understanding this one slide. We can learn about layer 2 and layer 3 right on this slide this week. So next week is a lot easier to understand. In our module 8, I believe, is next week. Not module 7. Module 7 is more of what we're talking about this week, but module 8 is the network layer. Okay, so here we go. So I want you to notice the different colors. The reason why they have different colors is because the NIC portion of your frame changes. Your PC has a NIC. You're going to do an assignment where you're going to look at NICs on devices. If you haven't already, you're going to look at the MAC address of the NIC on your device. So you have your unique MAC address on your network interface card. You know that address, and that frame is included. And you also know the destination hop, the next hop, not the destination of where your frame is ultimately your information is ultimately going to, but the next hop in the path between you and the destination. So this is unique. This is unique. This MAC address is unique. This NIC MAC address is unique. So when you send at layer 2, layer 2 is transferred from your MAC address to the device, your next hop, your router. And then at that point, if R1 is not the ultimate destination, then R1 repackets at layer 2, repackets that frame with its own source NIC MAC address and destination next hop MAC address, and it sends it out. If R2 is not the destination, then it repackets. That's what we talked about, how layer 2 encapsulates and then de-encapsulates. It encapsulates here. We encapsulate, de-encapsulate, encapsulate, de-encapsulate, encapsulate, de-encapsulate. It gets to the other side. Now, this device is the location. So this is the actual device. So it's there. And so now this device, if it's going to return information at this point, the destination IP address, these two switch if it's coming back to the original source. You click on an HTTP, remember the video at the beginning of the presentation? You click on a website, it goes out over the internet. On the other end, the web server flips the destination source addressing because now your computer is the destination and their computer is the source. Notice that L3, the layer 3 information, the source IP and destination IP, stays the same as it moves through all of the different addresses, all of the different nodes, each device it hits from point A to point B, from point A to point B. So layer 3 stays the same. Just like in a post office, your addressing on the letter stays the same. That's layer 3 from your home to the destination out in California or anywhere in the world. But the MAC address, all those individual post offices between your computer and the between your home and the destination, it changes as to the next post office, the next post office, the next post office. I hope that helps to understand. You really have to understand this concept. It's not hard. If you understand this concept, then this chapter, module 6, 7, and 8 are all easy, and then everything you learn later is just a little bit easier for you. So remember, MAC addresses are a change. They're layer 2. IP addresses do not change. They're layer 3 of the OSI model. Okay? I think I talked long enough on that slide. The local topology and physical media determine the data link protocol used, and that protocol could be Ethernet, 802.11 wireless. Now that Ethernet is Ethernet, the Ethernet that we've been talking about. 802.11 wireless, point-to-point, HDLC, frame relay. Basically, what is the media? Is it wireless? Sorry about that, guys. Is it wireless or is it wired? What type of media are you talking about? And that makes a difference in the presentation. Remind me to always turn off my volume before a presentation starts, okay? Anyways, that's it for this presentation. I told you it would be short and sweet. That is the presentation about MAC addresses. Let me go ahead and stop sharing my screen. My name is Don Lafond, Professor Don. Hopefully that was a relatively easy module to review. Remember that last slide. The second to last slide, make sure you understand that concept of layer 2 changing at each hop. Those are the MAC addresses. Those are the individual little addresses as it goes across the internet, where layer 3 is the destination and the source address, and that only changes if the information is coming back to you after it gets to the destination. If you have any questions about that or any of the assignments that are due this week, and there's several, please ask here in a moment if you're live with me, and I'll be happy to answer those questions. If you are watching in our classroom, ask your questions in the help discussion forum. And if you're on YouTube, please ask in the comments. And I hope you like and review my presentation. It's really important to me. And I will, I don't know, maybe I'll send kudos out to you someday in the future for that. I don't know, maybe bonus points for my students. Anyways, you guys have a great day, and I'll see you again in just a few minutes. We're going to cover Module 7, and you guys will probably want to roll right into it as well.